Okay. So I'm going to talk about physically clustering data in Oracle. So lots of us know how to design a database. You throw a few tables together, slap on a few primary keys, a bit of referential integrity if it's not a data warehouse where that's all banned. Stick on some indexes and there you go. And it will perform brilliant. And any Java programmers here? Because Oracle's just a box and it will just work. But it doesn't, unfortunately. And if you actually think about where you physically place your data, how you're going to group your data, you can read great benefits. And I think it's actually a bit of a dying, I wouldn't say dying art, it's just something you're not given time or bandwidth to do. So maybe I'm just shooting in the dark here, but I want to just present a summary of some of the ways you can cluster data. Okay, so a little bit about me. I've really been doing this for over 2 decades. Jesus. I've just fallen into jobs where I design very big systems. Biggest one I've designed eventually grew to half a petabyte before they got really scared and turned it off again. And I'm not really a computer programmer. I'm a failed scientist, genetics, I love cats, don't like computers, and in fact I'm retired. Or I was until about 3 weeks ago when a friend rang me up and said, can you come down into London and help? We need help. So I did, and as a result I am now, at the moment, utterly knackered and can barely stand because I'm not used to this working life anymore. So I used to be known as that VLDB genetics guy, and then that stats guy, now that annoying workshop guy. So, this used to be known as physical implementation. And anybody come across the term physical implementation before? A couple of nods. So when you've done your logical design of a database and you know what your entities and your attributes and your relationships are, you then actually say, well, how are we going to structure these tables? What table spaces are we going to put them on? Even what structure of table space are we going to have? Some of this has all disappeared because Oracle's made it redundant, but we used to do this step called physical implementation, and it included doing partitioning once you got to about 1997, and use of these strange things called clusters and IOTs and stuff. And I couldn't find any of the quotes because it got to about 1 o'clock last night and I ran out of whiskey and I couldn't be bothered searching anymore. But I do know that the likes of Tom and Christian and Jonathan Lewis have all said, if you're not clustering your data, you're probably doing something wrong. And I suspect Mr. Hall said something similar before, but
I'm not intelligent enough to say that sort of thing.
You wouldn't say that sort of thing, would you? Because the database is just a box.
Black box.
Yeah.
Replaced by Hadoop.
Oh, that reminds me. I need to take you to task about an article you're going to write next year that I'm going to criticise in a posting because I find
Oh, yeah, okay.
Well, in joke, sorry. Right. This is how Oracle looks up data. You have an index, usual triangular shape. One block read gets the root, another block read the branch, third block read, fourth block read. That's full of leaf blocks. Gets the row ID, goes straight to the row in the table for a fifth read. 5 consistent gets to get your data. That's how an index works. And that's how a lot of your data access is if you're using an index lookup. And if anybody remembers, last time I was here, I witted about the fact that there's 4 levels, so the B level for that index is 3, because Oracle hides some of the information, just confuses. If you have a range scan, one block read, one block read, one block read, and then you get to the leaf blocks and you do a little scan across it. So you get a 4th block read where you find the first record you're interested in. It walks along the index. Of course, these 2 blocks aren't next to each other physically, but they are linked by pointers. And for each record, it gets the row ID and it skips all over the table, selecting your rows. So when you do a range scan, you get 1, 2, 3, 4, 5, and then usually a block read per record you pick up. Yeah, because the data is just spread over the table. So, a normal index lookup is highly efficient when you're using a selective index. As soon as you've got more than a small number of table blocks, and it's about 6 because Oracle read all 5 blocks in one go if they're there. It's actually more efficient to use an index lookup than to look at a table, just scan a table. And in fact, if you bother looking at Richard Foot's stuff on indexing, you'll quickly realise that it's nearly always best to use an index than just read the table anyway. The larger the table is, the higher the efficiency of an index compared to scanning the table. That's because you only generate another level of an index for a massive increase in the table. It's exponential. I've never seen a healthy index more than 5 levels deep. And I've worked on massive, massive databases. However, a range scan gets less efficient as the percentage of data you scan increases, and also as your table gets larger. So if I just go back a sec, once this range scan gets up to about, for an average size table, about 1%, 2%, you're probably better off just scanning the whole table rather than doing this pick method to get it. Oracle does an awful lot of things behind the scenes to make reading large amounts of data faster, making full scans faster. One disadvantage you have, because if you do a full table scan, it's often not cached in memory, so next time you need it, you have to scan it again. So, the key considerations for efficiency in an index are the cardinality. Just sort of disappears, doesn't it? I'll just have to do this. I can point that up.
Can you point to the top line for me, please?
Which word do you want me to point at? Selective.
Oh, that's very impressive.
I can only do that 3 times and then I collapse. And that was heightest. I'm going to take you to terms for it. So, cardinality and clustering factor. What are cardinality and clustering factor? So, the cardinality is basically how many distinct values there are compared to the number of rows. Yeah? Unless you have histograms in place, and there are issues with histograms, completely different talk, but general principle, don't gather histogram statistics on columns unless you've got a really good reason to gather them, in which case definitely gather them, otherwise don't. And the way you tell the difference is you've always got it wrong and you'll have to change it. If you have 100 values for an index, Oracle will just assume that it will identify 1% of the data. And if more than one column has filters on, it does an additive thing by default. There are caveats to that. If your statistics level is set high enough or you create certain objects, Oracle will understand how columns really relate. But generally, Oracle says if there's 3% going to be fetched by that record and 3% from that, then it's going to be 0.09% or whatever. Okay. For indexes themselves, Oracle holds a number of distinct keys, so it knows the average cardinality of the index. So it's a bit more intelligent when you've actually indexed. By the way, did you all remember to turn off your phones? So I didn't. I don't think it's anything important. I think it's just my wife in America telling me she's still alive.
So obviously you see no police then?
I'm going to skip some slides. The words are there so that if you download the slides, which I've uploaded them, you can read them. But a demonstration of it. So, you've got the person table. It's got 1,376,000 records in, and you can see the distinct number of keys. So Oracle can work out the cardinality because they're indexed. And if they're not indexed, if you've just got the number of distinct values, Oracle just uses that. That's what Oracle uses to get its cardinality. But what's this clustering factor? Okay. Who knows what the clustering factor is? There's a couple of yeses, a couple of nods. The clustering factor is a magic number that tells you how well your index order matches your table order. And what it really is if you scan the whole index, here we go, if you scan the whole index, I'm just showing a little sort of snippet of there from the beginning to the end, what Oracle will do is it'll walk along the index, ding, 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 it'll go, right, I'm reading from that block, I'm reading from that block, I'm reading from that block. Oh, I've gone to that block. It increases the clustering factor count by 1. Same block. Oh, I've changed again. Increase the clustering factor by 1 again. Change the block, increase the clustering factor by 1 again. Then it does 3 reads without changing the clustering factor. Yeah? Now, the clustering factor will be between the number of blocks in the table, which is basically, it's perfectly walked through the number of blocks in the table, and only changed when it gets to the end of a block, and the rows in the index are perfectly aligned to the actual table. So it will be between that value and the number of actual rows in the table, because it means every time it changes the row, each time it walks along the index, it's actually going ding, ding, ding. I've got an example of that, yeah. So a very unordered set of data. It will read from that block, it will read from where the 2's got to, that block's so clustering factor increased by 1, increased by another 1, increased by another 1. Yeah? If it has to skip from block to block to block to block to block, the worst you'll get is a block change per row. That's your clustering factor. You can see how that logically works. If the clustering factor is close to the number of blocks, it's very ordered. It's very in line with the table. It's very near to the number of rows. It's not very ordered index. Matters not a jot if you're doing a primary key lookup. Matters like crazy if you're doing a range scan. Yeah? One thing it's not very good at, if all your data is adjusting one part of your table, and everybody thinking, oh, that's your recent data, or maybe he's thinking partitions here, it will go, skip, 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 skip. Still get a really high clustering factor, but all the data is in those few blocks and will have been cached. Yeah? So the clustering factor doesn't give you all the information you need. So just a bit of a warning there. Everybody happy with the clustering factor? Yeah? So that's probably a bit more wild than normally you have. That's probably close to how most indexes are. Yeah? The data is kind of worked on in the order it comes through. So, how can we cluster our data together? I'm going to talk about index organised tables, but nothing like as much as I usually do. There's a whole talk I do on index organised tables. Who's implemented an index organised table for real on a real system? 1, 2, 3, 4, maybe 5. Who's thought about it and then chickened out? Why? Why did you not do it? Sorry to pick on you or anything, but you, why?
For the reason you suggest, you look at it and you think, is that really worth the game?
Okay. Maybe, maybe not. If you look at my whole talk or on my blog about index organised tables, that'll give you all the information you need to know whether you'll get a gain or not. But there's still another factor why you might not do it. That is because there's only 5 people in this room who actually implemented it, which means it's rare. And if it's used rarely, that means it's full of bugs. IOTs aren't actually that buggy. But I'm going to come back to this topic briefly later on. Part of the problem with some of these technologies is they're not used very much, so they don't get used very much, so the bugs don't get found, so when you do use them, life is painful. So, what is an index organised table? The table is created in the standard index structure. Remember, that's the root node and 0, 1 or more branch nodes and then leaf nodes. And whole rows are inserted into the index structure. So the index is created and maintained as normal B-tree index, but in effect Oracle sticks the rest of the row into the leaf block. Instead of the row ID and all that, it has the rest of the row, unless you do various things to have an overflow segment, whatever. The order is maintained whenever you insert any records. So it's all looked after for you, just like an index. That has an overhead. Inserting data into an IOT is slower than inserting into just a plain heap table. But it's actually not that much slower than inserting into a heap table with a primary key on it. There's only about 15-20% difference, rather than the 150% difference between a table with no index and a table with one index. Did you all know that an index immediately adds about 150% overhead to inserting a row in a table? And each extra index adds the same general overhead. It's not a magic, it's not always 150, it's just more than the effort to insert a row straight into a table. Your IOT must be organised on the primary key, and that can be a little sticking point. There are ways around it. I cover it on my other talk in my blog. So in effect, you create the primary key, no table segments created, and all the data is kept in the index. I prefer IOTs because of my data hosting. It's not an index organised table, it's an index holding a table. Yeah. So this is what you in effect get. You've got your normal index, and underneath there's this massive chunk of table data that's plugged into the bottom. So you do 1 read, 2 reads, 3 reads, 4 reads. That's all you need to do to look up a value. There is your row, use your row. We've saved one consistent get. And in fact, this is sometimes talked about as one of the advantages of IOTs. It just reduces the number of consistent gets. Yeah, so otherwise you'd have to skip off to the table. Range scan. It's 1, 2, 3. Yeah. That's so much better than that. Because with an IOT, you find the point in the index where your data starts. You just walk along the IOT, collecting your data as you go. You have clustered your data physically together, so it's easier to get. And a quick example, that's how to create a simple IOT. It's all there in the notes. And you have to have your primary key, and just say organisation index, and tell it where to stick it. It creates an index, it doesn't create a table. If you try and look at the table segment, it won't exist. It confuses the hell out of me every time I do it. And I've been using these for years, because I'm thick. Then you just select your data from your heap. This is actually from the heap table I'm selecting from. It's the same statement for the IOT, except it says child IOT. And this is what you get. Unique index scan, go to the block on your row ID, 4 consistent gets. With an IOT, you just go to your index, 3 consistent gets. Just to remind you, the cost is 2, consistent gets is 3. Anybody remember why? It's because it's a primary key. And when you access by primary key, Oracle reduces the cost by 1, just to confuse you. Right. When you do a range scan with an IOT, or with a heap, this is the heap, you go to your index, and then you dot all over the place via the row IDs to get the records, 88 consistent gets. IOT, 5, because the index holds the data, and it's all in order. So IOTs come into their own when you do range scans. The system where I had the biggest benefit from this was where data was being pulled in over time for customers, and then they wanted to gather all the customer information together at the same time. It sounds like bank-like, doesn't it? And the reduction in consistent gets was about 30 times, because you weren't having to skip back and forth along the table structure anymore to get the records. They were all gathered together. 30 times less consistent gets, resulting in, I'm going to say 30 times less physical I/O, but hopefully I'll get onto that right at the end. The nice surprise on the physical I/O. Right. Who's thinking, why don't you just physically order your table so that your clustering factor's nice and healthy, so that, okay, it's having to go to the table all the time, but the blocks are always there. You're actually reading the same blocks over and over again. You can do that, and you do it by inserting into your child. You have an inner select and your order by, and insert into an ordered set, and you can do that. There's absolutely no problem with that. And you can If you're processing data in PL SQL, you can do exactly the same thing. You can actually select from an inner query which has an order by on, and it will preserve the order by. So you can, especially if you're staging your data and moving it into final tables, you can use an ordered insert to order the table into the heap, order the information into the heap table. It does work, it does help, but it's a one-shot thing. If you do any updates to the table, the records may move about. Okay, you have to do this religiously, and another problem is that unless you document it thoroughly, nobody knows that you've done that for that reason. And even if you have documented it thoroughly, depending on where you're working, sometimes the people you're giving them the document to, you know, aren't going to understand it, so you can't do it because they'll mess it up later on. So it's not an ideal solution. Use of partition swaps can really aid this. You order your data and then swap it in. Okay, so that's another way of clustering your data, ordered inserts. And I did an example of going from an ordered heap, and the consistent gets went down quite considerably. Right. So single row IOT benefit, I've said this before, you save around 16 to 33% per individual row select, which you're not getting a block. There is a slight chance your index will be deeper because you're storing more information in it, so it will flow a level quicker. Occasionally that happens. When you're doing range scans, it's not so good either. It's not as good as it could be because you've blown the size of the record, so not so many things in block. Your index is a lot bigger. So if you have to do a full index scan, it's much slower than IOT. Okay, so you get a bit of an increase, but there are better ways to actually get faster individual record reads. I'll get to. So fetching a single row by the primary key is faster than an IOT, and is often why they're implemented. But selecting a range of values is significantly faster. IOT should be used for giving ranges of data. There's something I call row payload. If your row is very, very large, you stick it in an IOT, you're going to end up with very few records per block. So either don't create an IOT with it, or think about moving some of that payload off into an overflow segment. You can Google overflow segments. I haven't got time to go into the details because this isn't a dedicated IoT tool. Oh, by the way, if anybody has any questions as they go along, just feel free to throw something at me and I'll raise your hand and I'll answer it. I'm conscious of the fact I'm just throwing words at you. You can get similar gains by physically ordering. Inserts are slower, but they aren't as slow as you think they might be because people usually test against an IOT and a plain heap. They don't add the primary key. Yeah. Now, admittedly, you can't remove the index from an IOT when you insert data, not the primary key one. You can with a normal heap. But day-to-day running OLTPs, the insert cost isn't so high. There we go.
Martin, you may get there in the slides, but do you compare IOTs to partitions?
Yes.
I guess more people use partitions than
Yes, I do. I don't talk about partitions so much because there's so better known, but I do touch on partitions right at the end. Other use for IOTs, and this is what I generally use them for in reality. We're losing Big Dave here. Intersection entities. So the only reason this thing exists is to hold the primary key of the person and the primary key of the count and to join them together. We all have lots of intersection entities. You usually create the table and then you have two indexes on it. Person account and account person. The table is superfluous. Why don't you just create it as an index organised table with one index on it? So create it with the primary key of person account, then create a single index on it with just account person. Then you've only got that one object. And you can save a lot of space. That's using a heap with two indexes. That's using a plain IOT, so you've actually saved space because your table's gone. Your indexes are a bit bigger, but your table's gone. Index organised tables, you can compress the index. save space. And you can shrink your IOT and save more. And then you can shrink and have compressed indexes. And you can end up using, instead of 263 meg or whatever, 152. So you can save space with an IOT as well. Just putting that piece of information in your head. Don't expect you to fully grasp the details, but if you're going to create intersection entities, you can actually make them a lot smaller and more efficient by using an IOT. Right. Who's implemented a table cluster, an Oracle table cluster for RIM?
On production.
Not on production, that's not for real.
It was a real VM.
Yeah, somebody once selected for it. You've done a real one?
Many years ago.
Okay. Hands up, and this is asking you a lot of you. Hands up everybody who doesn't know what an Oracle clustered table is. Good, somebody's admitted it, 2 people have admitted it, brilliant. Lots of people don't know what they are anymore. You basically create a cluster.
Jonathan does.
Uses clustered tables. Yeah, but he's beardy and weird. Oh, you're claiming weirdness as well as beard. So you create a cluster and you give it a cluster key, for example, number 8. And then you have to create an index on that cluster. Doesn't do it automatically for you, which is annoying. Okay. Then you create one or more tables and stick them into that cluster. And when you stick them into that cluster, you just say which column is going to be used as a cluster key. So you can quite easily see that you might use an order ID or person ID. What is the point of this? Oracle, every time it sees a new value of the key, allocates a block to it. And any records from one or more tables with that ID get stuck into that block. And it will keep sticking records into that block till it's full, then it will throw another block. Which means if you've created a load of order lines and you cluster on the order ID, they're all going to be in the same block of data. You've physically clustered your data together. Yep. When you select the data back for that key, so if you select all the records for a certain, it's just one table for a certain ID, you know they're all going to be in the same block and they're going to be fetched. If you often have a table with a relatively low number of sub-records and you're always joining them together, a cluster will keep the data together, and that join, Oracle will implement it by collecting the information from that block or blocks. This was one of the first physical implementation things Oracle built. I know that these were available in Oracle 5. It could be way back to Oracle 4 or 3, I'm not sure. They are extremely slow to populate and damn waste of space. You remember I said when you have a new key, creates a block, 8K block, sat there with one record in until you add some more. You know?
You can have more than one key in a block, I think.
I think you have to go to hash table clusters,
Okay.
and I didn't touch them because it's just too much. Right. This is an example. Create your cluster. Rather annoyingly, then have to add your index, cluster index, create a table person, cluster on the person ID, and I just selected it from my original person table. And I did it with a person name. I've got this state where you've got person, all the names they've been known by in all the table, your dummy database. They're all clustered together. I've got about 1.3 million records in there, and I had to reduce it to 50,000 because I got bored waiting for the segment to create on my laptop because it's so slow. And you see, it took like 21 seconds to do that 50,000 records, and 2 minutes and 27 seconds to do 50,000. I just shoved them into a heap, and it took under half the time. And you end up with blocks these size and those these size. So when I put it all into the cluster index, even though I only did 50,000 records, it's still pretty large. Yeah? I mean, this table's much bigger, but it's got, 50,000, 2 million records, big difference. Okay, so it wastes space and it's slow, but you can do it. And the payback for doing it, you just select all the surname, full names for a person that they've been known by. They're in heap tables in the standard way, joined by an ID, 16 consistent decks, consistent gets. You go to your various indexes and nested loop, join them together. If you do it via a cluster, you'll see this table cluster, table access cluster, big unique scan of them, merge join Cartesian, because it just knows, you can just whack them together, it knows that the set will have only records that match. 6 consistent gets. It's a lot faster. I don't understand why clusters aren't used more.
I do. The reason why is because no one spends any time going from doing the logical and physical design.
Yeah.
So you never really know what the tables are going to be used for until they're in production. And so making a decision about physical implementation, like a cluster or an IoT, gets difficult because they suddenly go, oh yeah, what we forgot is we're going to query on this as well, and we need these 14 other indexes. And all of a sudden you've got secondary indexes and IOTs, and it all gets a bit scarier. So because no one does design anymore, doing anything that's not standard tables and indexes can often dig a hole for you later. I would say that's why I'm sort of scared of them.
I can't disagree with you. I think you've nailed it pretty much. I think the way that I've struggled on to keep making a living in this business is by trying to do the database design and stuff up front, but it's becoming there. But I think you're right. IOTs, it's not such a problem having secondary indexes. They can become gnarly and unpleasant. Clusters, I'm not sure. And this is another reason why they're not used.
You
They're
do
not used
also
because nobody uses them.
You do also find that when new features come on board, invariably it will say something like, this is not supported on IOTs or clustered tables for the first 2 releases. Then they'll say, and now look, you can do it in clusters as well or something. So,
yeah, you're absolutely right.
So, sidebar to, it's not so much that people don't do designs. If you put design into a quote, then your manager will cross it out, the customer will cross it out, the customer manager will cross it out, and you'll get hauled over the coals for why are you trying to pad out your quote.
Yeah, whereas the ridiculous amount of post-implementation change and support is absolutely fine for the business, isn't it? I know what you're saying. Yeah.
That's just paid in gear.
Yeah. Yeah, it's
We
all
always do
about
paid in gear.
it's all about being countering, moving, and politics, isn't it?
Yeah.
Yeah.
and MongoDB doesn't need any design.
It's shards. It's fast as fuck.
It's web scale.
Have you tried just piping everything to dev/null? That's fast. Yeah. Okay. No one uses clusters. We all use clusters. They're in the dictionary. Oracle uses clusters. In Oracle, this is from Oracle 11. I haven't checked 12 because I'm just too knackered to download Oracle 12 and install it. My current client doesn't have 12 for some reason. Oracle uses clusters for a lot of its internal objects. So they think it's a good idea. Yeah? But then again, they also still have code in Oracle 11 which has the rule hinted.
And longs.
So you don't, clusters are used, but only by TPO people. Right, that's enough on. Right, single table hash clusters. Single table hash clusters are a bit like the famous £1,000 a day contract in London. They do exist, but you can never find anybody who's had one. Single table hash clusters are sort of famous. Anybody want to tell me why they're sort of famous? No? They give you the lowest cost to get a single record other than no ID. So it's a cluster of one table, single table hash cluster, and it's a hash cluster, which means instead of clustering an ID, you cluster on the hash of the ID. So Oracle just uses an algorithm to say if the ID is 123.5, the hash is going to be a magic little number. Hashing is just a standard thing you do in IT, and it means that given the value, Oracle knows exactly where to go. It doesn't have to look up anything. It doesn't have to work through an index. It just goes, If the source value is Widlake, the hash is gone, it goes there. I wish my ego was bigger. So it's calculated, there's no I/O, it's just a little bit of CPU. And the hash gives the block that Oracle needs to visit to find the record. In fact, positioning the block as well, I think. So long as you design the single table hash cluster to be at least large enough to hold all the rows. This is why they tend not to be used, because you have to do a bit of design, and you have to know how many records you're going to have and how big the records are. You can retrofit it. You can replace a table with a single table hash cluster later on when you've got the information, but then you have to have budget in your post application modification budget. Okay? If you undersize the cluster, it goes bad on you. Sorry. Doesn't work. So this is how you do it. You create a cluster, say you're going to cluster on this number, and you say size 50, that's the average size of your row. Okay? It's a single table, and it's going to have this many hash keys. So you've got to be confident that the average row size is going to be 50 or less, and you are going to have 10,000 records or less. Then you create the table using the cluster, and you're clustering on that ID there. Okay? And then I just inserted a shed load of data. Select the record. One consistent get. You cannot beat one consistent get unless you use query cache. But if you're actually physically collecting your data, you cannot beat one consistent get. That's almost as good as using the row ID. There's just that little bit of CPU on top for doing your hashing. However, here I gave the wrong number of hash keys. Now it takes 9 consistent gets to get the one record, which is significantly less than 4. Sorry, more than 4. And if I reduce the size of the row down, again you get more consistent gets. And in fact, if your rows are on average about 100 bytes, and you said there are going to be 50, the impact is worse. I suffered a bit from using a small initial row size, but there you go. And just a couple of things. Read can only contain one table, and you can only have 404 clusters per, 256 entries in a hash key per block, an AK block size. Do you think any of you are going to give single table hash clusters a go? I'm not going to ask you to try table clusters, that's just way too scary. I do know a few places which have used single table hash clusters for lookup tables you know are hardly going to change. For example, region. Yeah? You've got 200 regions in the area you're dealing with, or possibly even currencies. Okay, it's going to slowly change over time. But you can afford to overstate the number of hash keys and waste some space. Say waste, instead of using 8 meg for your table, you use 60 meg. Who cares? If you get one consistent get fetches, that's got to be worth thinking about. If you're fetching the information each time, that all adds up. Right. What was that saying about? Oh yeah, there's another reason. I'm talking about clustering data. This is another sort of clustering, it's reverse clustering. You're inserting records and they're not going to the leading edge of the table. They're spread over the table. There's no hot space. And if you're having trouble with things like interested transaction lists in blocks, so Oracle keeps track of the number of processors interested in rows in that block at a time in the ITL, because they're all at the hot end of the table. If you use a hash, you can spread that out. I've actually been to one site, I didn't implement it, some people far more smart than I did. They used some hash tables to push the information out across the whole table and broad, because they really needed those records really quickly, all the time, lots of times. Right. Partitioning, we're almost at the end. How long haven't I got?
15 minutes.
Got another 15 minutes?
Up to, yeah.
Flipping heck.
Shadows.
Right, I might do a dance at the end. You probably all understand what partitions are, and I actually struck a load of basic info about partitioning out of this talk. If you feel that that's missing and you would have liked it in, when you do your feedback, please just mention that, could you please have actually put some basics on partitioning in there, please? I've kind of assumed you really sort of understand what partitioning is. So the most common form of data clustering is partitioning, and it's often about managing a very large object. The table is just too damn big to have in one massive table, so you partition it up. And it's usually partitioned on date, or it's partitioned on an ID, a survey ID, or something like that. Sometimes they're partitioned on type of record, and you allow things to move in and out of partitions so that the active partition's always got a small data set. That's reasonably common as well. But basically, you're splitting a very large table up into chunks. If you do it on date, it opens the way to the old partitions. You can do things like you can compress the data, or you can drop them out of the database completely once they're over 7 years old. And you can put your most current partitions on faster storage. If any of you have got a hybrid storage setup where you've got some SSD and most of it's just spinning rust, you might want to put your latest partitions on SSD, and then every month you shuffle them backwards or whatever. Partitioning hardly ever helps with OLTP type access, because that's usually going via an index, primary keys, and an index doesn't get deeper that quickly as it gets wider. So partitioning is usually used to help manage looking after the table. The data warehousing, partitioning allows you to say, we're partitioning by month, because we know we're mostly going to work on that month of data, so that's our working set. Yeah, it kind of makes logical sense. And it helps that you're keeping your data in the SGA that you're working on. Yeah? Just one word of warning. Beware daily partitioning. A lot of places put in place daily partitioning. The reasons it's tricky is because unless you consider somehow handling statistics for the object, you'll have lots of problems with performance just suddenly going bang halfway through the day or something like that. Happens with weekly partitions as well. But small partitions, because they fill up the data really quickly in relation to their initial size, the stats go out of kilter and whoop, you're dead. There are ways around it, but you have to think about it, implement it. I'm not saying don't use daily partitions, just be a bit careful. And there's also good reasons for not having 16,000 partitions in a single database. It's usually been done by somebody who's done a bit of partitioning work and got overexcited. Right. So when you're partitioning, consider your data access, not your data creation really, your data access. You're thinking about how can you design your partitions to match your data life cycle or the data you usually process. And that might include moving stuff from one partition to another when it's stopped being interesting. Beware of over-partitioning. I'm going to quickly show you why. I pretty much said all that. Yes. You might choose a partitioning key. You might choose to partition on order ID because it makes sense, or you made a mistake. But really you're working on a date range of information. So your partitioning doesn't match what your where clause really are, what they usually are. Well, you can do something I call correlated partition exclusion, which is where you partition an ID, so you're going to give it an ID range to work on. Sorry, you partition by ID, you're working on a date range, but you can make either a very good guess or a damn reliable check to see what your range is within that and state that as well, and thus get partition exclusion. So this especially seems to be true in the middle of this last decade, so like 2008, 2009, I kept on coming across big databases where they partitioned on ID, but wanted to look at the data by date range. So they'd state the date range, and it would have to look at every single partition. So partitions were an idea, it couldn't help. So just by stating a really wide date range where the data had to be in there, but it was less than 6 months, it suddenly made their code perform better. So as an example, you've got this massive table, and your table states the end dates are 60 million, 70 million, 80 million, 90 million, blah, 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 as your days go by. These are the maximum values of date and time, that's your maximum ID. So that code there will probably perform terribly because you're giving it a sys date range and you've partitioned on ID. So you can just add an extra clause where saying order is greater than select the max table minus 30 million. So you give it the top of the range for the ID. It can't possibly look at a record more recent than that. So you add that in there, and that stops all considering all of those partitions. It only looks at the ones up here. Yeah? And you can do it, you can say between this value and this value. You know you want last week's data. You know how many records per month you get. You can do a calculation and do it this way. So you can give it a correlated range, and it will partition through. That could be just a little bit too unstable for you. So what I did for one client is I created a tiny, tiny table which held the min and max. And they added that in a join in the where clause. So they collected those two values from the lookup table and used those as further where clauses. Their performance went from terrible to almost good enough just by doing that. And it's physically grouping your data, of course. This is what partitions are partly all about. It's physically grouping your data. Right. Partitions are rubbish and they slow your database down. You want to select a single record from a huge table. This table is like 6 gig, because that's how big was when I wrote this slide. You go down, I put like, how many? 1, 2, 3, 4, 5, 6 levels of index. Flipping heck, that's a big index. 1, 2, 3, 4, 5, 6, 7 reads to get your record. Yeah? Then you partition it up. And I've only got 4 partitions. Okay? And the depth has gone down to that. But you don't know what partition it's in. You're not including the partition key in your query. Okay? So it goes 1, 2, 3, 4. Is the record there? Yes, fine. 1, 2, 3, 4. Is there a record there? Yes. 1, 2, 3. Yes. No, there isn't. That's a lot more consistent guess than that. That's 7. That's about 15. Yeah. And that's a good scenario. The situation I first came across, there was only 1 record. So for most of the lookups, it wasn't finding the record. It's okay. It's just a quick index lookup. It doesn't matter. It didn't matter in the first week when we only had a couple of partitions. It didn't matter in the next week when we had about 10 partitions. A year and a half later, we had about 400 or 500 of these partitions, and nobody had looked back or noticed. And I was just doing a look at the database and looking what the most demanding code was. I was thinking, that's selecting 1 record. Why is it doing about 3,500 consistent gets? It's because it's having to check each partition to find the record. Yeah? So when you do put in partitions, for goodness sake, try and catch code that's not using the partition key early. And if that's happening, correlated lookup. Right. This is the bit, this is the killer bit. I really want to go, yes, this is fantastic. I'll show you ways to reduce your buffer gets, your consistent gets. I think the most significant way you improve your performance is by reducing the amount of memory, working memory, you need to hold your working set of data by making it all in the same place. You can do this with partitions, you do it with IOTs, you do it with a mixture of IOTs and partitions. Caching rows you don't actually ever reference is a massive waste of space. You do not want to cache data you're not going to look at. So, what do I mean by this? This is how a lot of our systems work. You want a relevant record, you go to your block, gets pulled into your cache, you only want that record. All the others you don't care about. But you don't care because it was only like 4 or 5 persistent gets to get there. But that record is now in your SGA. And your SGA is stuffed to the gills. I mean, I didn't change the colour. In these, there's only 1 or 2 yellow ones in each one. There's a yellow one there, there's a couple of yellow ones there, there's one yellow there. Damn, didn't change the colours.
Oh, you can see the difference. You can see it.
Thank goodness. So, your eyes are better than mine.
John, I can't see the difference.
We were magic.
Come back here, you can.
Right.
No, it's me always. Turn the light on.
Just plug into your Jedi, feel the Force, find the bloody colours. Right. So really, honestly, only 1 or 2 rows in each block is coloured yellow. And the rest of it is what? It's data you're not going to look at. You don't give a flying about it. It's there in your SGA. So your SGA is mostly consisting of dross. Yes? Collateral data. I'm trying to get this phrase to be used. It's collateral data. It's along for the ride. 95% collateral data. You have an index organised table, and you could do this with partitions as well, because if you've got a partition of just your day's worth of data, most of those records you're going to process that day, or reprocess that day, it's putting in blocks which are consisting of all of, or mostly, the data you want. Yeah? So what's in your SGA is your working data set. Now remember I mentioned that system where the I/O was reduced down to about, I think it was 1/20th or something of what it would have been if it was just one massive heap. Well, the real killer was the person before me had designed it to also be massively partitioned, so that they were having to look down each partition to find all the information they wanted. So it was having to do those 3 or 4 block lookups each time to get each record and put it across, rather than just having a much wider index for a month or whatever. So reduce the persistent gets. But then I calculated how big the SGA would have to be to hold the working data set now, because we physically clustered the data together in blocks. And before I did this, our SGA at most could count about 10% of the working data set. By clustering the data, now the SGA was going to hold significantly more than our working data set. We were actually able to reduce the SGA size and still get a buffer cache hit ratio of 99.99% or something ridiculous. And buffer cache hit ratios, of course, are completely pointless, except for it proved a point that we were only referencing data in memory. And so instead of getting a 20% reduction in I/O, sorry, a 20 times reduction in I/O, we got something like a 99 times reduction in I/O. And if you pulled up, fortunately I couldn't find it, if you pull up the OEM graph of that database, there was just a little green line at the bottom with the occasional spike. And the occasional spike was? It was Oracle making sure it was okay. It was actually OEM collecting his data. And that was a live system doing a lot of work. Okay. That's where I stop. So, you cluster your data to reduce IOs. You can use single table hash clusters to get really fast IO by using partitioning and perhaps IOTs if you're a bit braver together. You can cram your active data set in memory more efficiently. Now, there's all other sorts of considerations about if you're doing full table scans and things, it doesn't get cached and you might need to use the cache in, but basically, fundamentally, you can actually get rid of all that collateral data and only have the data you're interested in memory. Any questions?
Which is more expensive, partitioning license or extra payment?
That depends how good you are at negotiating. You
Yes,
use
a big factor on that is that with hardware the way it is these days, every time you buy a new bit of kit, you get a lot more cores than you had the last time. And all of a sudden, unless you're going to use some form of virtualization that supports like reducing your core count, then you're going to find that the next hardware refresh, you owe significantly more to Oracle than you did the last time.
Another way to answer your question is I've been involved in a few projects where they've looked at reducing their license costs by going down to standard edition, but there's nearly always been a sticking point, which is they didn't want to let go of partitioning. You can't have standard edition without partitioning. I don't think there's any internal logical reason why you can't. I think
You mean
Oracle
the other
still
way round?
use it. No, so you can't have standard edition with partitioning.
It's an enterprise
Even
option.
though,
It's enterprise only.
if you look at the data dictionary in standard edition,
But it's a different thing though, isn't it? Because that's partitioning system, not partitioning user. If you look at the feature usage on it.
yes,
So-
yes,
but
that's
yes, it's there.
but that's really sneaky and
Yeah.
slimy of Oracle to see it that way. Anything else?
I'd be interested, assuming money weren't the barrier,
Yeah.
which of course it always is, be interested to run all of this again, but then comparing with, say, Exadata, where you've got smart scans getting rid of a lot of your collateral because you're only sending back the columns and the rows of data that you care about, so you're thinning out all that stuff. And I'd also be interested to see with this new in-memory malarkey, because then how much of that stuff can you select just the bits that you want and say, keep these in memory anyway, so I've reduced my I/O cost.
The in-memory is particularly interesting, but with the Exadata, all that filtering only kicks in with full table scans. And with most full table scans, it never goes into the SJ, it goes into your PGA.
Yeah, but you're not impacting on your compute nodes, are you? Because that works. If it's a smart scan, it's all happening in the storage cells.
Yes.
So, I mean, I don't know because I've never
Yeah.
used Exadata, but I'm just wondering if you're running the numbers of the effort of clustering and maybe partitioning compared to the effort of just saying, oh, we'll full table scan it and let the storage node do
Yeah.
the work, and then comparing that to the in-memory. I wonder which ends up being easiest.
It would be very
Probably the most
interesting.
expensive version, in-memory and Exadata, probably.
However, I would make a prediction, which I'll probably never get to prove or disprove, which is the testing on Exadata, which suggests Exadata is going to be a lot better, because when you test on Exadata, people hardly ever put a real workload on there. So when you do full table scan, Oracle uses as much storage power as it can to answer your question. And they don't consider the fact that you're going to have to scan again, and again, and again, and again, because it's not caching the results unless you take some step. So my gut feeling, having worked a bit with the Exadata box, is initial testing would show it would win, real life would show it slows down an awful lot.
But is that because you're talking about like a consolidated OLTP load, as opposed to like, say, a data warehouse where most of the queries will be unique, so caching isn't that big a deal?
No, it's the fact that you're just running a reduced work set on the hardware.
Oh, sorry, got it. Yeah.
So you get the whole of the hardware to work for you.
Yeah.
But then when you've got 10 people trying to do a massive great full table scan of a huge record, Oracle can only give you 10% of the I/O across all of the storage nodes. Suddenly everything's a lot slower. And I've been badly burnt by that one.
I think Greg Rahm's talking about that, and he's just like advocating the parallel statement queuing and just saying don't let more than 3 queries run at any one time. But yeah, take your point.
Yeah, but it would be an interesting experiment. Anybody got any other questions? Brilliant, thank you.